Hey Mr. Mod, I focused my project on the chemistry of saponification reactions, which is essentially the hydrolysis of an ester, normally an animal or vegetable fat, with a strong base to form glycerol and fatty acid salts, also known as soap. The two bases most commonly used are sodium hydroxide and potassium hydroxide. Generally, sodium hydroxide is used to form hard bar soaps, while potassium hydroxide is used in gel or liquid soaps. A saponification reaction can be described as either a one- or two-step process. The one-step process is when a triglyceride, mixed with a strong base, splits its ester bonds to release glycerol and fatty acid salts, resulting in a crude, lower quality soap. The diagram in the next slide will be a good example. In a two-step process, which is more complicated, the hydrolysis of the triglyceride outputs a carboxylic acid rather than its salt as seen in a one-step process, along with glycerol. The alkali, a base dissolving in the solution, producing hydroxide ions, neutralizes the fatty acid to produce a higher quality soap. In this reaction, the two reactants are ester and alkali, while the main product is a carboxylate ion, an acid that carries a negative charge once its proton is removed. The hydroxide ion from the alkali molecule becomes attracted to the electrons of the ester or fatty molecule. The OR group of the ester becomes a leaving group, with OR referring to an oxygen atom bonded to any molecule R. The OR group departs, forming a double bond and creating a carbonyl group attached to the carboxylate ion. The OR group removes a proton from the carboxylic acid, a process known as deprotonation, and carboxylate and alcohol are formed as the final products. I specifically focused on saponification reactions involving the formation of soaps, which is the primary purpose of saponification in industry and manufacturing, as well as in handmade soaps, which are more consistent with the historical use of saponification when animal fats were mixed with vegetable oils to create primitive but effective versions of the soaps used today. In my demonstration, I used sodium hydroxide, NaOH, and olive oil to produce glycerol and sodium palmitate as seen in the little diagram there. This produced a substance resembling bar soap rather than liquid soap, which is made with potassium. Something I should definitely also mention is saponification value, which is simply the number of milligrams of base required to saponify 1 gram of fat or oil. This value is important when attempting to create soap and must be considered in order for the reaction to be as effective and efficient as possible. Saponification values are most commonly given for potassium hydroxide, so these values must be converted when sodium hydroxide is used by dividing potassium hydroxide values by the ratio of the molecular weights of potassium hydroxide and sodium hydroxide, which happens to equal about 1.403. In this case, I used olive oil, which has the potassium hydroxide average saponification value of 190 milligrams per gram of olive oil. So the sodium hydroxide saponification value is 190 divided by 1.403, which is 135 milligrams. This number is dependent on the properties of the triglyceride. Those with longer fatty acid chains have relatively fewer carboxylic functional groups per gram of fat as compared to shorter chain fatty acids. So the longer the carbon chain of the triglyceride hydrolyzed, the lesser amount of acid released per unit mass, and the lower the saponification value. So for my demonstration, I performed a saponification reaction using a sodium hydroxide solution and olive oil to produce a crude form of hard soap. I chose to use a 9 molar NaOH solution and only 10 milliliters of olive oil for the purpose of this reaction, taking a minimal amount of time to complete. The first step was to correctly form the 9 molar NaOH solution using solid sodium hydroxide. I didn't have a beaker on hand with exact measurements, so I had to go with a mason jar that had approximate markings for 100 milliliters. With some simple stoichiometry, I determined that 36 grams of NaOH was needed, so I added the NaOH to the jar and filled it up to the line with water. The reaction was also clearly exothermic and generated a lot more heat than I was anticipating. In this next step, I apply the sodium hydroxide saponification value of 135 milligrams of base per gram of olive oil. It can be determined that 3.5 milliliters of NaOH solution is needed to fully saponify 10 milliliters of olive oil. And that's a 9 molar NaOH solution. Now, using some graduated cylinders, I measured out the olive oil and added the sodium hydroxide solution and stirred for about half an hour until the mixture became very pudding-like in texture. I then added just a dash of stearic acid, which is a waxy fatty acid used to better solidify the end product. As seen by the photos, the soap became harder and drier over 2 weeks' time until it had the stiffness and texture of a common bar of soap. The end result was a sodium palmitate glycerol mixture which can be used as a moisturizing hand soap. The hydrophobic tails and hydrophilic heads of soap molecules form structures called micelles, which trap non-polar substances and clean surfaces of dirt and grime. However, I decided not to test the soap for myself because I did not want the possibility of getting any undissolved sodium hydroxide on my skin, which can cause severe irritation.